Hi, I think I know most of you, but for the folks that don't know me, I am Rajit Atapattu and I'm the Cto of Randoli. Prior to Randoli, I was at Red Hat for about 11 years, about 9 years in engineering, 2 years in consulting. Been writing code since about 18 years, been in the industry for a while. Especially in the last 15 to 20 years, I've been very fortunate to be involved in some really large-scale applications and had the privilege of seeing kind of what works and what doesn't. And one of the things that I've been always a big fan of is the event-driven paradigm. And I've seen a bunch of horror stories, but I have also seen where it really works, provided that it's done right, with the right kind of architecture, with the right kind of tooling, with the right kind of mindset. It can work really well. And yeah, it's becoming a bit of a trendy topic again because of microservices and Kafka, but this is not something that's new. It's been done way before. Oh, it just got messed up. That's okay. It's been done way before microservices or Kafka came along. It's a tried and tested approach. And like I said, it's becoming a bit of a hot trend right now because of microservices and Kafka. So it's got a little bit messed up, but that's fine. So we have 2 sessions planned out. For the first half, we are going to talk a little bit about the architecture. What exactly an event-driven architecture looks like. We're going to talk about some of the challenges, some of the areas to keep in mind. We'll look at best practices and some patterns that we can use when we implement an event-driven architecture. And then hopefully I should be able to finish that before the break, but just because people are getting a little bit maybe hungry or towards the dinner time, so we'll try to stop around like 6:20-ish. If we haven't finished, because this is the area that I want to definitely go through all of the content. So if for some reason we can't finish everything, we'll just continue soon after the break, and then we'll talk about the hands-on part, which is how can we use Kafka and Camel to build your event-driven microservices and why they are really suited to building applications that way. And hopefully when we get to the Q&A discussion, if you have questions, great. But what I'm really looking for is hopefully if you have you're doing this or you're trying to do this and you have questions or you have comments or have feedback, it'll be great if you can share your user stories and ask your questions, and we can have a bit of a discussion going, and hopefully all of us can and learn from it. Just before we go to the other one, like what I really wanted to achieve out of this, when I started planning for the event, I was talking to some of you, and everybody was saying that, we're trying to do this. It'll be great that we can talk and bounce some ideas. So if we can somehow, at the end of the day, if we all go home having gained some insights and tips, that's what I want to achieve out of it. I'm not here to try to sell you anything or convince you to use A, B, C or any kind of product like that. But really what I want is for you to go with some sort of insight that can help your current initiatives. Even if you're not doing microservices, like I said, the event-driven paradigm is equally applicable in outside of the microservices context. It's fine if you're doing a monolith. You can still use some of those concepts. So hopefully it'll be a useful session. Most of you have something like this, and you are trying to. Most of you have either a monolith that you're trying to migrate off and thinking about doing microservices, or it could be a blank slate. It's a greenfield application, so you're trying to build from scratch. So either way, you're thinking about going to microservices. But we all like to hate the monolith, but when we move to microservices, we have a picture like this. So I just try to put together a rough sketch of what an order processing system may look like. Now, right off the bat, there's a bunch of differences that you would see, right? Number one is that what used to be a local method call is no longer a local method call. Now it's a remote call. So that brings in some complexity that was not there before. When you talk to another service, that could be available or it may not be. It could be unavailable for a short period of time or for an extended period of time. The network may be choppy, the network may be down. There's all kinds of error scenarios that you have to think about and deal with, which you didn't have to when you had just one big application, because everything was either available or not, right? So now you have these error conditions that you have to worry about, and it's not like anybody who has done any kind of remote method calls, it's not it's not that easy. You have to write a non-trivial amount of code to actually handle these situations, right? So that's just one thing. The other problem is before, like I said, it's either the main application is available or it is not. It's either or situation. But with this situation, some of these services could be available, or some of these services may not be. So you have what you call partial failures. Now that can be a blessing too, in that you may be able to fulfill some of your serve your customers and fulfill your API calls, but that introduces some other complexities. Because of partial failures, now you have to deal with inconsistencies in your application state, right? So it's a blessing in one hand, but a lot of headaches on the other hand. So you have to worry about how to manage your state and how to keep things in sync. Obviously, local transactions are slow, but distributed transactions are even worse. So how would you coordinate and orchestrate across a whole bunch of microservices, which is not trivial, because before it's all in the same code base, a bunch of local method calls, not anymore. Yeah, we were talking about the different error scenarios. So yes, I was referring to, I think I shouldn't touch the clicker too much. That's probably what caused it. So if you look at over there, there's a lot of point-to-point type of connections, and a lot of dependencies that you can see over here. Now, before, like I said, it's all within the code base. So if you have a mess, that's fine. It's contained within that code base. Here, there's a lot of point-to-point connections, and if you are doing so, the popular way of kind of handle, with microservices is to use REST interfaces, right? So what that means is you're going to end up with a lot of REST calls. If you're talking to one or two, sure, it's fine. But let's say today you're talking to one or two, but tomorrow the order process service may need to fit something else in the middle, or it may need to talk to yet another. So now you're going to talk to three services. You got to make sure that you are able to communicate to all three, and handle any kind of error scenarios, because chances are that two will work, one will fail, or or I don't know, all will fail. So there's different combinations. So, and from an application perspective, you have to figure out like what does that mean? Can I still continue? Do I have to roll back? Do I have to do something else? So there's a lot to kind of think about and coordinate too. And also your network chatter is going to increase a little bit. There's a lot more going to be on the network as well. So a lot of complexity is going, and I think this is bad, right? And yeah, please. And this, this can give you nightmares, I guess. So this is an actual visual representation of the microservices at Uber. So they're using a lot of it, and like I said, we all, we know the benefits that microservices brings to the table. We all know the, why we want to do microservices, which is why I didn't even talk about it, because this is 2019 and everybody's heard about microservices. Everybody knows what the advantage is, but it also comes with a lot of complexity, and untamed complexity can cause a lot of issues. And this is why there's a lot of other methods of taming this complexity is becoming popular, like service meshes. Like I'm pretty sure all of you have heard about service meshes, which helps you deal with some of that issues that I talked about. Whether it is handling policy, security, circuit breakers, rate limiting, versioning, etc. Service meshes can kind of help with that situation, but also at the same time, it's not trivial to get a service mesh going. It's not kind of easy to get all of that going. So, are there any alternatives? Can we use other approaches to handle some of this complexity, right? And as I mentioned right at the beginning, I've seen how the event-driven paradigm works. And like I said, it's been used even before microservices came to the picture. And certainly it's becoming popular again because people are finding that, maybe doing a whole bunch of point-to-point, REST calls may not be easy to manage. It may not scale very well. So let's try an event-driven approach. Now, I'm not knocking off REST. There's definitely a time and place for that. If you have services that are outward facing, you definitely need REST interfaces so that outside applications or your front-end applications can talk to. But within like behind your service layer or within that, you can certainly use an event-driven approach to kind of handle and manage that complexity. All right, so yeah. Okay, so people have started using microservices, and now they have a bunch of questions, right? Like I said, the partial failures we talked about, the decoupling is certainly an issue because now you have a lot of point-to-point interactions, and your services are kind of coupled. You want to, you need a way to kind of handle the dependencies, etc. We already talked about, what should we do if we have to communicate the same piece of state to multiple services, that kind of stuff. Before we kind of move further, out of curiosity, how many of you are actually using microservices? How many of you are either whether it is production or in the dev stage? Just curious to know. Yeah, you guys are using, yeah? No? Matthew? Yeah, getting there? Yeah? Okay, cool. Anybody has used the event-driven approach before? No? Oh, yeah, there you go. Maxis, yeah. Yeah, the concepts, absolutely, yeah. So let's look at what we can do. I mean, we'll continue to use the same example and see how it may start to look like when we try to bring in some of the event-driven concepts, right? So, let's look at, right at the beginning, the way the interaction started was a client application placed an order on your order API, and before it was, as soon as we got that, we created another outbound REST invocation into your service layer. But instead of that, what if we model that particular order received change or the state change as an event, right? And I can then put this event in some place, like a queue, message queue or a Kafka topic, and then let others, next slide, let the other services who are interested in this subscribe to it. And what we have done here is we've kind of invented we kind of flipped the dependencies. Instead of the order API calling the order processing system, the order processing service or anything else that might be interested in the order received event, I am just only going to be worried about creating an order received event, putting it somewhere that others would know where to find it, and leave it at that. And then whoever that's interested in it can subscribe to that event. Now we kind of flipped it, but and let's look at like what are the implications of doing this, right? Like all of a sudden, the code that I need to write in my order API is becoming simple, because now I no longer need to worry about whether the order processing service or the audit service or whatever is available or not, because I don't care. It's not my responsibility anymore, right? So I will, all I care about is I receive the event and putting it in a message queue or a topic or a Kafka topic, and as long as I am able to put that safely and the messaging system says I got it, then my responsibility is done. And I can tell the client application we've received the order. So if you notice, like maybe 10 years ago, or even like 5-6 years ago, when you buy something online, usually you hit buy, and the browser kind of is now kind of stuck waiting for something to happen, and maybe in a minute or two, it'll tell you like, oh, your order is submitted, it's all good, right? But try now, like what do you see now when you try to buy something, right? When you submit an order, usually within a couple of 30 seconds or so, you get a response saying, oh, we received your order, right? And then in maybe 2 minutes, 5 minutes later, you get an email saying, hey, we've processed your order, or we processed your payment, or if there's a problem with your payment, it will tell you, oh, there's a problem with the payment. And then come Black Friday or some of the busy shopping periods, that email won't come for 15-20 minutes, sometimes 30 minutes. What's going on? It's because some of them have kind of implemented this pattern where when they receive it, as soon as they receive it, instead of trying to process it right off the bat, they've taken it, put it somewhere on like a topic or a queue, and then acknowledge the customer saying, oh, I'm able to receive it. Now, right off the bat, you'd see that there are some benefits here. For example, if you look at the, go one more slide, one more, and I will, no, go back.
Oh, sorry.
Go one more back. Yeah, no, one more back to the, oh, sorry, my bad. I think I
deleted something?
No, it's fine. I just wanted to show that it's okay. Go forward. I think it's forward. My bad. One more. Yeah, go on. Yeah. So we'll go back a little bit. But here, this is the synchronous invocation, right? Where we used to take it and try to process it, at least partially, before responding. And if any one of these systems are unavailable, we may or may not be able to do it, and we'll say, you know what, we can't do it, right? And then during a really busy period, what starts to happen is that your order API, because anytime you do like a synchronous invocation, you start to realize that your application threads, especially if if you have a bounded thread pool, will slowly start getting busy. Right? Sooner or later, you've exhausted your thread pool, and you're no longer able to fulfill the next request coming through. So either you have to drop other incoming connections, or your client is going to, your client application will continue to pound your application. Eventually, you'll crash too. Or if it's a poorly written application, your order API, you'll continue to just spawn threads and try to hit the backend, and soon either you will go out of memory, or one of your backend systems will fall apart. That usually results in really poor customer experience, or worse, you're going to miss a lot of business. So about a year ago, I was helping one of the postal technology, I don't want to say the name, but they had this problem where come Black Friday or closer to that period and leading up to Christmas, some of the large vendors like Amazon or other large retail giants would place orders for delivery, and they will just dump in like large numbers that they don't normally see during regular time, right? So sometimes their volumes are double compared to the average volume. So it's like it's kind of hard to plan too, right? And in a situation like that, when you have outages, the retail applications that is sending this also starts to back up, and they'll start yelling, "Oh, we can't process our orders. It's affecting our customer experience." It was a really bad situation for this postal technology company. So what they did was, and that's what we helped them with, was to move to adopt some of this event-driven approach, where when you get these requests, you safely put them on a queue. Sure, your backend systems may be slow, they're trying to still catch up, but that's fine. Give them some breathing space to catch up, but you're not disappointing your customers. You're not disappointing your partners or your other entities, business entities that are using your API. So you're able to get all the requests, and maybe you're a little bit slow, but you are able to handle everything. You're not losing anything, and you're able to not lose any business. So let's go back 2 more. So I think we talked about this part where we model some of our state changes as events, and then we trigger microservices based on those events. Now, when those microservices also when they consume these events, they can create their own events, and then eventually what we'll have is they will produce some events, and then the ball keeps kind of rolling, right? So what's essentially happening is you're going to model your application flow or your business as a continuous stream of events. And I mean, if you think about it too, like if you look at in your most businesses, it's really a stream of events, right? Like you have a purchase order created or an invoice created, a customer making a transaction, like making a payment, or issuing a refund. And that's just like that's something that has a direct business value. And there's also other events that does not have a direct business value, like someone logging in, like an employee logging into a system, or a security event like an intruder getting into your network, or a developer making a commit, or creating a customer creating a Jira ticket. So these are all events that a business may care about. So when you start to look at it that way, if you look at all your interactions that happens within a business as a series of events, then it kind of gives you a natural way of how you can model your systems based off that, right? So that's why I feel like the event-driven approach, it's actually, when you look at it, at least from a architecture perspective, it's easy to reason about, because it's kind of easy to wrap your head around it and try to model your systems based on that. When it gets to implementation, it's a little bit more complicated. We'll talk about that, but at least it's something that I feel like it's easy to model. It's easy to reason about. Yep, that's okay. So like I said, what's the big deal about this? And we kind of talked about it. I jumped a little bit ahead of this. So we talked about the synchronous approach and why it's causing issues, right? And we already talked about some of the challenges that you as a developer has to deal with, right? You have to worry about handling all the different error scenarios, worrying about interactions and state changes and all of that. So by using an event-driven approach, you're trying to simplify your code. Now, one thing to keep in mind is that complexity is not going away. It's just that you're offloading that to someone else. And that's going to be the messaging systems, whether it is a traditional message broker like IBM MQ or ActiveMQ, or something like Kafka, like a distributed event log like Kafka. But here's the thing though, rather than you having to write code and deal with this, why not you offload it to someone who are presumably experts in that domain, right? It's their day job to really build systems that, like messaging systems that scale and provide you the reliability guarantees that they advertise, right? So yes, the complexity is not going away, but at least it's not in your hands. So you're giving someone else the responsibility, right? So that's something I want to kind of, because sometimes when I work with customers, like, oh, it's all easy, but no, that complexity is going to someone else, and if that can't handle that, then that becomes your point of failure, right? So let's take that simple interaction we we looked at before and try to look at some of the benefits that comes with an event-driven approach, and hopefully that will lead us to the patterns that we're going to talk about, right? Okay, so right off the bat, we see that we have an event stream, could be a queue or a Kafka topic that sits between your order API and your order processing service, right? And this has a number of benefits. Like I talked about, if the order processing system is slow, it gives it a chance to catch up while your order API keeps on taking orders. If the order processing system is down, as long as your messaging system can handle and keep those events safely, when it comes back up, it can start handling those events again. And the order API is fairly simple, as we talked about. It doesn't need to know who's going to process it. All it does is put it there. And for the order processing service, on the other hand, it doesn't care where it is coming from, whether it is coming from an API or wherever it is. All it knows is if I subscribe to a particular event stream or a queue, I am going to get some orders and I need to process. And then similarly, like we talked about, once it processes it, it can also create the outcome, and then there could be other services that are acting on it, right? Next slide. All right, so we already talked about this. Now, just to kind of emphasize a little bit on this, if you've been writing code, whenever a service is unavailable, there's a number of things you have to do, right? First of all, you have to figure out whether this is actually an extended failure or not, which means that you have to worry about doing some retries, potentially with the time delay. And then after a while you figure out, oh geez, it's not available, so what am I going to do? It seems like it's gone for an extended period of time. Maybe you have to think about some alternative strategy, right? So just the simplification, the code simplification alone, with not having to deal with that, I think is a huge win, because now you can focus on really implementing your business logic instead of having to deal with your error handling situation. Another thing that what you'll start dealing with is, now you can do this with APIs too, not an issue, and especially with service meshes and other technologies kind of helping here. What if you want to do a new version of your order processing service, right? You want to deploy a new version of it. Again, because the two sides are completely decoupled, the order API doesn't even need to know that there's a change that happened, or if there's multiple versions of it that is running, right? So it immediately gives you that flexibility to independently evolve either side without you having to even worry about what the other side is doing. And also, they could be written in different languages. They could be implementing, even different formats. As long as you publish that message in a format the other service can work with, even if it doesn't necessarily understand, can do a transformation and get it into a format that it can understand. But it completely decouples the two sides, right? So that's another advantage that this brings to the table. Reliability and fault tolerance. I kind of talked about this a little bit already. If for some reason your order processing service or whoever that's supposed to act on that is down, you don't want to lose messages, right? Whether if it is an order or if it is some sort of an important event, you just want to make sure that when I come back up, I need to be able to process those messages, because otherwise that can have unintended consequences, or it could actually result in a financial loss for your business. So the fact that you are able to reliably communicate that piece of information downstream is really important. Now, if you had a synchronous communication, then if for some reason, if the order API is not able to pass it on reliably, you'd have to, it's kind of hard to do transactions at rest, right? So you have to either throw a failure to the front end, or just not do anything, and drop the request, or you have to figure out how to write it to somewhere like a database or something. So obviously you can do some stuff, but it's again, you have to write the code to handle that exception situation, right? Here, the messaging system or the eventing system will give you that reliability or a safe point where you can put it and go away, right? Scaling independently, that's another one, especially when you're dealing with high volume situations. What you want to do is maybe closer to the peak period, you may want more services that are taking in the order, right? Now, if you didn't have something like an event stream, if you had this point-to-point communications, if you just still you can scale the services, with Kubernetes really easy, just scale up your pods, but that also means now you're going to put too much load on your backend, right? Sometimes you can scale your backend. It's not just a matter of scaling those other services, because you may have legacy applications and other applications that actually need to process things downstream. So beyond a certain point, you can really scale up some services because you will bring them down, right? But at the same time, you don't want to limit stuff in the front end either, because you want to continue to accept your requests. So what can you do? I mean, with event streams and message queues, right, like Kafka topic or a message queue, you can scale up one side independently of the other, right? And then let the other side slowly catch up without having to be overrun because you've got a huge load, right? I mean, this is another very easy pattern that you get with the event-based approach. If you're doing REST services right off the bat, now you have to call 3 services, right? That's, like I said, I have to worry about failures. You got to, tomorrow you add another service, then you got to go and write the code to talk to that, and that's yet another REST call to worry about. But with this kind of model, it's just another subscriber on the topic, and off you go, right? Again, yes, it'll increase the load on the maybe the messaging system, but that's their problem, right? That's their problem to solve, not yours. And it will give you a very easy way to kind of grow your system without having to worry too much about how you're going to manage those complexities and interactions. Before I go too further, are any questions on this? Matthew, you have a question? No. You sure? Just kidding. Yeah, good. So, I forgot one other benefit. If you look at something like Kafka, and this is a very nice benefit that you have. If you're, you may be holding up some state, and usually what happens is when you're processing messages, sometimes you want to batch things, so you consume a whole bunch of messages, and you somehow do some action on it, and then you say I'm done with it, and you commit. But with that comes a bit of a cost, because if your service crashes, then you're going to lose, because that's not being safely committed somewhere, you're going to kind of lose that state. So it's a real nice benefit with messaging is that the ability to replay, right? You can go back and try to replay from the last commit. In fact, with Kafka, you can even go, you can manually set the offset and go as far back as you can, as long as the retention policy hasn't, the retention hasn't caught up. That's available, right? So as long as the Kafka cluster retains that, you can go back and replay anything. There are a couple of systems that actually use this pattern, at its core. Can someone tell me what that? We use it every day. Most of us know it. Who knows that use this at the core of it? Everybody, how many people write code on a daily basis? Yeah, it's quite a few people. Yeah, and I'm sure some of you have written code at some point in your life, right? So what uses this pattern very heavily?
Git.
Huh? Git, exactly, Git. Right? Git is essentially a distributed commit log, and at any point you can move back and forward, because it gives you that ability, and you can replace straight, right? Like your state again. So that's one. There's something else that people in the bank should know. There's another system that we use every day. that use this approach, right? Huh? What's that?
Database logs.
Well, that's sure, but I'm looking more for like actual use case instead of a technology. Like, what do you do though when let's say, like, does the bank only maintain your account balance as like a counter, or does it maintain actually a journal? Exactly, yeah, right. Like all your transactions, nobody's deleting them, right? It's actually a series of debits and credits. So eventually, if there's an issue, you can go back and replay them or like go through them again, whether it's audit or for compliance or whatever reasons, and you should be able to rebuild your monthly balance at any point, right? It's not just a database field somewhere that says this is your current monthly balance, right? So you have probably running totals to serve that balance or whatever faster, but obviously there is a journal like an append-only log that's backing everything, right? So even though maybe you haven't used some of these patterns or these basic building blocks, this is not something that's kind of alien to us. Either we are implicitly using it, or we've done some of these things in the past, right? So
this pattern, many of the products won't even support, and the Kafka supports.
Yeah.
IBM MQ.
But the problem with the traditional message brokers is that usually when I say I read that message, it deletes it, right? But however, it kind of you can't really go back beyond the commit point. But if you don't commit, though, let's say I have 1,000 messages in the queue. I read 100. But I haven't committed it yet, and I crash. But when I come back up, those 100 messages that I read should still be there. However, halfway through, if I said, oh, I committed 50 or whatever, then that usually is gone, because that's how the traditional message brokers work. Kafka is different in that it's just advancing the pointer, and each consumer will have its own pointer. And as long as the retention policy hasn't caught up, your data is still there. So that difference is there. Yes, absolutely. Yeah?
You mentioned about service mesh several times. The service mesh right now is all synchronous communication.
Correct.
Yes, all synchronous.
Yes.
So when you talk about this, how does it coexist?
That's a very good question. So there is a couple of approaches that people are experimenting with, right? Because like you said, the service mesh is very it started to kind of support that point-to-point very synchronous communication because everybody was using REST. But how can an asynchronous communication mode kind of coexist with it? Do we even need a service mesh? Can we do without it? If you're using a service mesh, how can it help, right? I mean, I've seen a couple of approaches that have been floated around, and some people are looking at like an event driven service mesh or an event friendly service mesh. But again, what they're trying to do is either you're still sending a message, but the sidecar will take that message and make a REST call, which is not probably true event based approach, or the other way around, where maybe I'm making a REST call, but the sidecar obviously is going to intercept everything, but it takes that and actually sends it out. So maybe you're not even doing messaging, but behind the scene it's kind of doing messaging, because the sidecar can now take that message. I think there's already, I can't remember Envoy is actually, there is a side project that's going on where it's taking, it's like an HTTP to AMQP bridge. Anybody heard about AMQP protocol? Yeah, so there's some work that's kind of happening around. But yes, I think in the next couple of months or so, we'll start to see more people talking about it, because how are we going to do an event-based approach with a service mesh? But those are the approaches that I've seen being floated around. Where either it's like a bridge-based approach. Either your message to HTTP or HTTP to whether it's a synchronous communication or not, it's just kind of like going to do the bridging between the two protocols, right?
Question I have is,
Yeah.
HTTPS is very lightweight, right? REST is very lightweight. So if you add Kafka in there for every single microservice communication? Does it impact the performance, or is it okay? Like, do you advise using this for high performance application, or not?
If I understand your question correctly, your concern is that if instead of using like a REST-based approach for communicating between your internal microservices, what if you use something like Kafka, right? I may be a little bit biased, but because when I was at Reddit, I worked in the messaging team, and I've seen a lot of message-based applications, and they are some of the most high-performant, high-volume applications, anywhere from stock exchanges to applications that power banking to financial industry, heavily used messaging. Even way before Kafka came in, IBM MQ has been like a workhorse forever. If provided you set up your messaging infrastructure properly, usually it can handle volume. We're talking like 3 weeks ago, I just concluded an engagement with a customer in the US. They are a subsidiary of one of the large card processing vendors. They just used a bunch of ActiveMQ brokers, and they were doing like 70-80 million messages during the peak time, right? So it can handle millions and millions of interactions as long as you set up your architecture properly and your brokers are able to scale. And when it comes to Kafka, we already know that it can handle massive scales. It has a model where it can scale linearly. So I'm not too worried about scale. But obviously, as one thing to kind of think about is, when you talk about performance, throughput is one thing. Latency is another ball game too, right? Especially what you notice is when in an approach like this, messages that are queuing up behind will start to have more latency. So in certain situations that may or may not be acceptable. And also something that I didn't talk about, and maybe we can chat a little bit when we get to what are some of the issues. Sometimes you want to process some events in a timely manner, right? So by the time you get to that event, because you're trying to catch up, that may not be relevant anymore, right? That event may be not relevant, or whether your system or something else that triggered that has already moved on from that point. So there are issues like that too that you have to worry about. With a synchronous situation, either you can process that invocation or not, but at least it's like you're not, latency it might impact your ability to process others, but for the one that you're trying to process, at least it gets to it sort of like quicker instead of you having to queue up, right? So that consideration is there. Yeah. So yeah, if anybody has done anything asynchronous, that's one of your number one challenges, right? Like because before it might be hard to code and whatever, but at least I'm talking to this service and that goes here now, and it's kind of easy to kind of debug that. But because you can maybe use your debugger and have some stuff on the other end. But what if it's all event based? Now there's infrastructure piece that's in the middle. How would you debug, right? If I send an event, who got it, and how many people or how many services got it, whether they all consumed, how would you know all of that, right? It's really hard to reason, and this is one of the reasons why especially an asynchronous, like an event-driven approach is tough. Matthew, you remember the problems we had with that the event approach with BRMS, where events started firing, right? Yeah. So the problem is, because everything is very asynchronous, and you create something and some event fires. Now, if there is another service that may be listening to it, it might start thinking, something happened, I need to act on it. But it could be that there is a bug. Now, trying to figure all of that is really, really hard. And this is where I think a lot of people struggle with, and a lot of the efforts that I've seen gone south starts, that's like kind of like the core of the problem. As soon as it gets to that level, then you're wondering like, what can I do? How can I pull it back? And then either people go back to being synchronous, or they try to do other stuff trying to prevent this. So what can we do? There are a few things that we can do to work with. One is obviously distributed logging and tracing. So if you are doing so before we had monoliths, so few applications to worry about, but when you have a whole bunch of microservices and you're using event-driven approach, God knows what's happening. So you really need to implement at the least some distributed logging. So you know which application created this event, who consumed it, was there an error? If so, what was the error? Again, going back to that postal technology application of work, there's a lot of, we wrote a whole bunch of integration pipelines as microservices, about 60 to 65 integration pipelines. And they all act on a life cycle of a parcel. When a parcel comes in, whether it's like a postal outlet or someone who's on the truck, who's using a handheld scanner, delivering it to you, or whether they scan it and put it in the truck, all of those are events. And all of these events are now sent into the data center. And then these integration pipelines take these events and try to consume them and transform them and put it into a backend, which was their SAP, or there's other systems that were involved. Now, at any given time, we had to figure out for a particular parcel, which events came in, what happened, did we process them, were there any errors, did they get inducted into SAP or into the database? So trying to figure that out without any kind of distributed tracing is impossible. This is even worse if you use containers, because with containers, the containers are ephemeral, right? So just because you write, like in the past, like with monoliths, you can go and snoop around the log and try to figure out what happened. This you can do with containers, right? Because unless you mount persistent volumes, which is probably a bad idea to do when you're doing containers, what you want is some sort of a distributed logging where your Kubernetes is either you are directly writing to Splunk or Elk, or you use Kubernetes to kind of forward some of these logs into. You have like a bunch of daemon sets that are actually listening to the Docker logs and forwarding it into a distributed event ingesting system like Elk. You definitely need that, and without something like this, it's going to be a nightmare, especially if you have a lot of microservices and you have a lot of events that fire as a consequence of it, right? Any questions on this before I move on to the next one? No? So I wish that was the end of it. There's a lot more when it comes to the event-driven approach. A whole bunch of stuff to deal with. One is what I was talking about with Matthew is unintended consequences. So without naming any application or the company or whatever, a system was built where you had service. It wasn't a microservices type of application, but it was like a rule-based system where, again, similar concept. When something happens, some rules fired, which are events, other rules can fire as a consequence of it. Same problem. Very hard to debug. There's no logging. And beyond a certain point, the hardest part was like to track why certain rules fired or why some events fire. So that unintended consequences are a huge thing if you don't have proper developer discipline or a proper design and architecture to kind of understand what those consequences are and what you can do to prevent that when you go into an event-driven. Duplicates, I mean, if anybody has worked with messaging, duplicates can happen, right? With replay, whether it is Kafka or whatever, it could be that you process some of these messages and you crashed before you were able to commit, or you were in the process of committing, right? So you've kind of done something in the database or something, but you try to send the acknowledgement and you crash. Kafka didn't get it, or the message broker didn't get it, so they're going to replay when you come back. So now you have a whole bunch of duplicates, and you need to deal with that. So that's another downside to worry about. Um, I already talked about the state carried by the events, being stale or being out of sync with the actuals. So especially with an event-based system, you'd have to worry a little bit about consistency, right? It's kind of hard to do. So you'd have to think about eventual consistency, because there's a chance that, especially when the event itself carries some state and it keeps progressing downstream, things may have changed, and either because of a bug in the code, or it could be because of actual events that happened that you didn't plan, or it's actually there's no bug or really nothing out of the ordinary happening, but just pure luck and time. Because, like I said, it's asynchronous, which means that sometimes it's hard to guarantee your ordering. So things can happen out of order, and all of a sudden you have things going out of sync, which also is out of order events. That's something that's very very much a problem when you build messaging based systems out of order. Obviously there's ways to guarantee ordering, but the moment you start putting these restrictions in, then it also affects your scalability, etc. Right? So it's a bit of a trade-off, but that's something that you have to worry about. There are some events that you don't care if it is out of order, right? Maybe you have a way of reconciling it, but there's other situations where out of order events is an issue, and you have to make sure that you have to either the application needs to worry about how to deal with out of order events, or you have to get your infrastructure, your messaging infrastructure, to guarantee some sort of ordering in the event stream that you get. Lost messages is the worst, because that means there could be financial consequences, customers being upset, a lot of issues. So, but it can happen in the sense that it may not be an issue with the messaging system, but I've been involved with several messaging systems that actually lost messages, completely gone. The system acknowledged the producer or the consumer, but it's either because it couldn't handle the journal file was corrupted, right? Because the way the message brokers do Kafka, etc., is Kafka has extra copies too, but the file can get corrupted, the disk can crash. So if the messaging system does not have the right kind of architecture, or there are issues with the right kind of issues with how you do fault tolerance and disaster recovery, you can lose potentially a lot of messages, right? I mean, there have been entire data centers failing, disks crashing, all kinds of issues. So that's something to worry about and plan for. Any questions on before we hit the patterns? Yes?
Do you encounter any challenge on event data? Like, since it's distributed, we don't want to couple each other. We completely decouple. We don't want to one consumer try to go to source system directly to access the data. How do you carry data along the events?
So, yeah, that's a good question. Actually, that's one of the patterns that I want to talk about. So maybe we can, so I think the most simpler one, so that's exactly your question. One approach is when I get my order, actually I probably should move out of it so people can see. I don't know if this will work, but
It's just don't try that, so we don't.
Yeah, I know. Yeah. So when the order API creates the order received event, one approach is this event is just a notification, right? So I get the order and I write it to my database. Whether it's Mongo, MySQL, whatever you write to database. And when the order processor, whoever gets that data, wants to, I get the notification, but I want to know what the data is, I go back to the database to pull it out. There's advantages to this model, but as well as disadvantages, right? The advantage is you have one source of truth, right? So you always go to the database to get the latest source, right? So it helps with your consistency issues, but the problem is every time you get an event and you do something, it's a database hit, right? Sooner or later, that can cause issues too. So you want to think about what can we do to kind of handle that. In some situations, this might be the best way to do it, right? You might have a performance hit, but at least it solves your consistency issue. So the second approach is a pattern called event carried state transfer, right? So what you are doing here is, sure, I'm writing it to database because you obviously have to put it somewhere, and you try to put your data, at least enough data for the next guy to the next service to process it. So some of the state is carried in that event, right? If for some reason this next service needs some extra information or need to go to the database, it can do so, but it doesn't need to. Is my point. And some systems are built in such a way that the state keeps getting modified. So let's say you get an order. It's a JSON payload, and as you process your order, you keep manipulating that payload, right? So whatever that gets passed to the order processor may not be what gets passed down the line, right? Because now you have to update some state saying, oh, I verified the payment, or I did some checks, so I updated the loyalty system, or I talked to the inventory and the orders. So the state keeps changing, right? But again, because of either out of order processing or other stuff, that state that you carry may go out of sync with your source of truth, because every system too, when it gets, obviously, as in addition to modifying that, you probably want to update your database too, so it might go out of sync. So that's something to worry about. So what some applications would do is they have some sort of a time limit, and they will, at certain points, it's like a checkpoint, they would go and read from the database to make sure that there are no discrepancies, and they reconcile. And then you have to always assume that your data can be stale, so you have to have that assumption. But if so what that means is, for certain services, a slight inconsistency may not matter. But for other services, you have to absolutely have, so you can probably use like a mix of the two strategies, where when you get to a service that absolutely needs to know the exact current state, it should go to the source of truth, which could be your database or an SAP or whatever it is, and grab the latest data and then act on it.
It's a caching strategy.
It is. It's essentially a little bit of a caching strategy, because either you cache it in some other layer or you cache it in the event itself. Yeah.
But in this pattern, your order API itself has to connect to two different services. One is the queue and the database, right? So in that scenario, you have to implement a two-phase commit, right?
Yes. Good. Very good question. Yes and no. Right? So there's multiple ways of doing it, right? So one problem with the anytime you do a two-phase commit, like a distributed transaction, is super slow, right? And when you have to do a lot of that, eventually it becomes a bit of a bottleneck, right? There's multiple ways of handling that. So one approach is, first of all, we have to understand what are the consequences are that Shri is talking about, right? I can write my order into the order database, but I can crash before I write it to the queue. Or if I write to the queue first and I crash before writing to the database, that's a problem, right? Now you have like a bit of a discrepancy in your application state. So there's a couple of ways of doing it. One is, and we'll talk about when you get to Camel too. One is you try, one approach is to use transactions, which I try to avoid as much as I can. However, what you can do is maybe you write to the database first, right? And then you try to send it to the queue, right? So you're not doing transactions. You write to database. You try to send it to the queue. Now, when you try to send it to the queue, maybe the queue is down, right? So that's so one way to solve that problem is having a highly available queuing infrastructure. Like you have a highly available database, right? Replicated across maybe two data centers. There's all kinds of ways to handle it. That's one approach. So you're relying on your underlying infrastructure to be always available, but anything and everything can go wrong if you're involved in software. So what's the other approach? you can try to write n number of times. Like, you can retry. Like, I'm going to try 3 times to put it back onto the queue, right? Maybe I'll sleep for a little bit and try. So you're able to do it, no problems, right? If that's the case. But let's say you couldn't, right? Either the queuing system is crashed or you can't do it at all. Then what you can do is you can take a compensating action. So that's another way to handle, and that compensating action could be that you write it to a temporary database table, and you have another process, right, that actually reads that and try to put it back onto the queue. So that's one strategy. Or you actually go and modify something in the database itself, saying, something went wrong by when I try to put it downstream. So if anything else that's looking at that database already knows that, oh, there's a bit of an issue, right? So then they can look at what other compensating actions that they can do to resolve this issue, right? So by doing that, you can try to avoid transactions, because if you think about it, we are doing transactions, but that's just kind of for a rainy day situation, right? And you're paying a big price for it. So if you can avoid it by trying other strategies, then it's better to look at those. There are some situations though, like for example, maybe in banking, where there could have to use transactions and there's no way around it, right? In a situation like that, yeah, sure, you kind of SOL, but otherwise, there are other options like what I talked about, doing a compensating action, those retries, etc. For that same, I'm going back to that same postal, I'll talk about 2 examples with actual customers. When there was concerns about the MQ installation not being able to handle the load. What if it is, it's great, we take it from the REST interface and put it into the queue, but what if the queuing system has an outage, right? So a couple of options were floated around, and I didn't like what they wanted to do, which was they wrote to a file system. So they wrote all those entries into the file system. There was another process that looked at it and kept on retrying. Yeah, obviously another approach is write it to a database temporarily, because you need a permanent storage to kind of handle it. Because the one thing that we should do when building software is always plan for failure, right? Anybody read that book, Release It? Mike, I can't remember the last name. That's a great book that actually talks a lot about these kind of situations. And the big message in that book is, anything you do with software, doesn't matter what your intentions are, how well you're designed, things are going to fail. And you have to plan for that failure, right? And so, it's great to rely on the messaging system, but you have to have another strategy if and when that fails. And yeah?
Another one is the client itself can actually store the data before. When you get a commit from the API in that is success,
yes,
then only you delete from the client.
Correct. Yeah. So some clients are able to handle it. Like, it could be, I don't know, it could be like a front-end application from your own organization. Maybe you have some flexibility. It may result in poor customer experience. The customer will be upset. Oh my God, I can't do whatever I want. But it might be so that can be actually an acceptable strategy. Like, both your systems are, you can handle it, throw it back. But with some other situations where you can't really tell your partner who is giving you a lot of business, I can't handle it, right? So then you have to do something on yours. So there's different options of doing it. The other customer story that I was going to talk about was, they use, this is that subsidiary of the large card processor. What they do is, when they get some of these events, they try to replicate it into the other data center. Now again, with messaging, things can get lost, things can crash. So there's always a discrepancy, and you can. There's no way of doing transactions across 2 data centers anyways. So what their strategy is, they have a reconciliation process that runs every now and then they reconcile the 2 sides. So this there's options outside of transactions.
Do you want to take a break?
Uh,
Take a 10-minute break, or do you want to go through some?
I think there's kind of one more I want to, actually, yeah, let's talk a little bit. You guys are fine to talk a little bit more and then take a break? Yeah, that's cool. You sure? Yeah, okay, cool. So the other third pattern is, you already talked about this, event sourcing. And this is one of those other patterns. And there's a guy by the name of Craig Young, I think, who came up with this pattern. So if you, Martin Fowler is pretty big on this pattern, but the person who actually I think came up with this, Craig Young, this we already talked about. There's a lot. There's systems that we know and interact on a daily basis use this pattern. This is a great way to kind of, if you're trying to rebuild state. It's maybe not be for everything, but there are some systems that has to rebuild their state. Maybe they may have to go back and rebuild from, not just the last 1 hour, maybe last day, last week, last month, that kind of stuff. But this pattern allows you to go back and rebuild, provided the messaging subsystem is able to keep your records intact. And the other pattern that I wanted to talk about is command query responsibility segregation. So notice there's no diagram or anything. That's because this is for two reasons. One is I haven't used this pattern enough to talk about it and to even kind of talk about consequences and other corner cases. Second, this is also something that is hard to get by. So I'll explain the pattern very quickly. What at the core of it, what it does is you have two models. In your system, you maintain two models, one for writes and one for reads. So command is like the writes and the query is for the reads, and you segregate the two models. The idea behind it is that when you, for let's say even for performance reasons, you see like some applications use two different databases for this, where your writes happen on one database and you have a separate database to read. And sometimes the read database is not even an actual database. It could be like a Redis instance, or it could be like a Cassandra or something else. Like it could be like a caching system, something like it's in memory, or it could be actually a real database. So the customer situation that I was talking about before, they do that replication is because they get some entries, but their reporting happens on a separate database. Because a lot of customers log in and try to see what happened with their transactions, they wanted to completely segregate that load. Now, the problem with that is that there is a bit of a lag. Like I make a transaction, it's not like it's going to be available in the other database immediately, but that's still fine because it's better than everybody trying to pile into the same database and everybody, the whole thing crashing. Now I won't be able to even do a transaction, right? So that's kind of what the basic idea is, and it kind of and like I said, I haven't used that with that. Although that approach, you can use it outside of like an event-driven approach. There's a way you can combine this with event-driven approach, but I haven't used that, which is why I didn't want to talk about it. Yes?
Yeah, I want to add a little bit on what you said.
Yes.
Performance or other things maybe you want consideration, but we're mainly driven by microservices.
Yes.
Distributed system of record. So domain-driven design, you will have one domain handle one data,
Yeah.
other domain handle another data.
Yes.
Now you want to have a cross-domain view. How can you do that?
Exactly.
This is
the way. Yes, exactly. And I've seen that's one of the domain-driven design is probably one of the approaches for doing this. But it, like you said, it does come with some caveats. There's always there's no way of it has to be eventual consistency, right? Because it takes some time lag between the two. It might be a little bit complicated to implement, etc. So yeah, but if used right, it can really help because, again, like you said, the source system, you may get the records in a certain way, but when you're showing it, it could be different. So maybe the other model that is showing the data may need to transform that in a slightly different way or enrich the data, from somewhere else. So it's kind of like you're maintaining two different models. Yeah. Any questions on this before we get on to the next section? Or rather, actually, we probably should go to I have another one for the second part. So maybe it's a good time to, go for a quick break, like 5-10 minutes, and then we can come back. There's a lot of food because a few people didn't, well, not a few, I think. About 30% didn't show up. So there's enough food and coffee, and we'll start, like, what's the time right now?
6:30.
6:30. Okay, so we're kind of like right on time. So maybe we'll start around 6:40 or so, yeah?
What's the next section?
We're gonna so in the next section we're gonna look at how to take some of this and like use or rather how Apache Camel and we'll talk a little bit about Kafka too, and how Apache Camel can help you implement event-driven microservices and why it's a good choice to implement that. We talked about some of the complexities about like handling errors and etc. So I'm going to talk about what Apache Camel brings out of the box, and show some code examples too. I know not everybody's coding, but for the people who are coding, it's a good way to see that how it will help you to implement some of this stuff with less code. And if you're not coding, if you're like a senior manager or an architect, it'll give you a sense of what kind of productivity and efficiency these components will bring to the table. So that's what it is. Yeah.
There's lots of food outside.
Yeah, tons of food. Yeah.